Hello, everybody. Good morning. Good morning. I see Tabin's here. Good morning, Tabin. Um, yeah, first day with you and me actually learning a new lesson. Well, it's gonna be kind of a little bit adding on to the review from last week, but I'm pretty much picking up where Miss Lifshitz left off, and hopefully this helps you all. And the format of the notes is actually based off of Miss A. So it might be familiar to you guys from the format, which is great. That's something you're used to. So hopefully that helps you kind of ease into taking the notes. But good morning, everyone. It is two. Oh, it's not even good morning. It's good afternoon. It's 2 p.m. We have 7 people watching right now. We're gonna wait a couple minutes for a few more people to come in, and then we will get started. Good afternoon, Matin. So if you have any classmates that that you know are still asleep or are not joined into this video, please tell them to come and join us. My email address is this one. We're at 8 people. Just gonna wait a couple more minutes and then we will get started. I don't think today's lesson is significantly long. And I do want to clarify some things that I said last week. No problem. I'm glad I can help with that. Yeah, feel free to use that email for asking me any questions, and I'll try to respond as soon as possible. If I don't respond, just follow up with an email the next day. Don't worry, you're not being annoying. Just be like, hey, I sent you an email. I didn't get a response. Could you reply? And then I'll reply. So don't feel like you're being all like pushy. No, that's fine. Sometimes it may slip my mind. I'm preparing a lesson or I'm doing something else. So please feel free to email me again the next day if I don't respond, and I will try to get back to you as soon as possible. Let me take a look here. You sent me another email. Okay. All right, just one more minute and then we're gonna get started. One more minute. So hopefully you have this sheet printed out here. On your screen you should have this printed out. So if you don't have this printed out, please print it out and we're going to get started on it. If you don't have a printer, just copy these questions on a piece of paper as best as possible. And you just got to kind of follow along as best as you can. That's kind of the only option you have. Like the worksheets are all available on Google Classroom, so that shouldn't be an issue there. But if you don't have a printer, like my previous students have just copy down on notes on a piece of paper, and that's how they kind of work through it. So yes, you might not be as organized on it, but it is what it is, right? You just got to copy the questions and then copy the answers as I write them down. All right, let's get started. I don't want to wait too long. We have 10 people out of 30. That's good enough for now. So last week during the review session that we did on Friday, we talked about converting exponential form to logarithmic form and back and forth, right? What was the connection between the two? How do we convert between the two? So on and so forth, right? So we talked about how exponential and logarithmic functions are inverse functions of each other, right? And so if you have one, you should be able to convert it into the other, right? So the connection here, this first connection, if this is the exponential form, the logarithmic form should be log base a of y is equal to x. So just to kind of show you where the positions go between these two, right? This is like the most important form you should remember, right? The base a stays as the base a in the log. The answer to your exponential becomes the inside of your function, and then the exponent is your answer in the logarithmic function, which is what we talk about inverse, right? The location is different, right? It changes location where x and y should be, essentially, is another way you can think about it, right? So if we have that and we take this into account and we reverse it back to our exponential form, right? The answer should be 100 is equal to base 10 of 2. And of course, that answer should make sense. 10 to the power of 2 is equal to 100, right? That only makes sense. Now, this connection should be eye-opening for you, okay? And what I mean by that is that if you can understand that this is the inverse of the other, I had a question last week, like, can we even graph logarithmic functions if you can't do it on a calculator? And I said, the answer I gave was, you can't solve logarithmic functions on a calculator if their base is not 10. That's what I said. However, I never stated that you couldn't graph it. The main thing you have to understand is that whatever x and y you have for your exponential, you just flip it for the x and y for your logarithmic. And you know that as the definition of inverse. So if you know that inverse functions are pretty much flipping their x and y values for their points, as long as you know the exponential form, then you should be able to graph the logarithmic form as well. Okay, so it's a little awkward and different, but it is definitely possible. It's just a very roundabout way of doing it. You're essentially plotting or figuring out the points for exponential and then plotting the logarithmic. Okay. So here, last one here, 2 to the power of 5 is equal to 32. Converting that to logarithmic form, I'm going to start off by writing log base 2. I always write the base 2 first. And the answer is 32, so the exponent is 5. So I'm switching the place of the two numbers. Okay. Are there any quick questions here in the chat? I think we're good. Just give a couple seconds for people to respond if they have any questions. If not, let's keep going. So some key concepts that we need to know. Okay? A logarithm is an exponent. That's the whole point. We're saying these are connected to each other. You can convert one from the other. It's just the inverse function. And point number 2, what this actually means, like what's the log base a of x? Which means, what is the exponent that has to be applied to base a to get the value of x, right? So it's the flip definition of an exponent. The the exponential function definition is what exponent, or actually, it's pretty much the same definition, right? What's the value of y when you have an exponent of x with a certain base? It's essentially the same definition, except the location of x and y are different. So here, if you have an example of log 208, essentially is the exponent is to be applied, to base 2 is 3 to get the value of 8. That's essentially what this means, right? So if you have base 2, to get the value of 8, you need an exponent of 3, right? We know the answer is 3. So that's, and as you start using logarithms more, you're going to get comfortable with converting back and forth, right? Even for me, when I review it, I'm like, wait, what's the rule again? Oh, that's right. And you kind of remind yourself, and as you get comfortable, you'll get better. So let's talk about evaluating these logarithms, right? Let's evaluate these logarithms. You're gonna see easier ways of doing this as we progress through this chapter. Like the next chapter we do is called laws. Next section that we do is laws of logarithms, and that's gonna help understand these concepts better. So let's use the basic ideas that we know so far. Okay, so essentially, right, we have log 4 of 64. Oh, how do we solve that? Right? What you can do to solve this is to say, oh, if that's equal to x, can you convert that, right, to your exponential form? So if you convert that to your exponential form, we should get 4 to the power of x is equal to 64. Once you have that, right, you are going to be converting it into a common base. So what is 64, right? To if we use base 4, what do we have to use for 64? What exponent is it? So essentially we're saying this is this, which means it's 4 to the power of something. Anyone have the number in chat? Anyone want to type out the number in chat? What exponent should go here to get 64? Anyone? Four to the power of what is 64? We don't got anyone responding, so I'm going to give it to you. It's 3. 4 to the power of 3 is 64. Perfect. Matten posted it. Very good. So 4 to the power of 3 is 64. So now since we say the bases are the same, for this equation to be true, that means the exponents have to be the same. So we, in the end, we write that x must be 3. And there we have it. Right? So that's how you solve it using a common base. You can convert, right, these things to another. So let's go through a couple more examples here. Okay? Let's go through a couple more examples. So log base 3 of 1 over 27. So if we equate that to x, right? We're saying 3 to the power of x is equal to 1 over 27. Let's make our life simpler. We don't like having fractions for many people. So instead, I'll write 27 to the power of negative 1. We can convert 27 to a base of 3, which we would get 3 to the power of 3 to the power of negative 1. You should know your exponent rules. Exponent to an exponent multiplies the two together. You get 3 to the power of negative 3, which means my final answer is negative 3. Okay. So if you, once again, going through that process, we equate the beginning to x. We change it to our exponential form. I personally change the fraction to an exponent of negative 1. And then I convert the 27 to base 3. And then go straight through. Usually this shows my steps better for people to understand. If you go straight from here all the way to 3 to the power of negative 3, that's fine. Because that's true, right? You understand that 27 is to the power of 3 already. And since it's a fraction, and the 27 is at the bottom, you know that it's flipped, right? So that would be the negative. So 3 to the power of negative 3, and then you can equate x equals negative 3. Okay? So there's our answer for this one. We'll go through one more. Log base 2. So the answer, the question is log base 2 of negative 4. Log base 2 of negative 4. If we technically do it like this, so if we try to do this, right, we would get 2 to the power of x is equal to negative 4. Is that possible? No, it's not possible. That's right. You can't make exponential functions into a negative, so x does not exist. Right? Undefined or does not exist. Right? It's impossible to make negative 4 into a power of 2. Right? So there we go. So good. We're getting answers there. Now, of course, there are complex numbers. We're not going to get into that. But if you search like on online websites, they'll give you some random number with i's in it. That's nothing to do with our course. If you get anything that's equivalent to a negative number when it's in exponential form, it doesn't exist. It's undefined. All right. So I'm going to give you this one here. Okay? I'm going to give you 3 minutes to try these two and solve these two on your own. Okay? So 3 minutes. Give it a shot. I'll put a timer and I'll play some music in the background. And we'll reconvene. 3 minutes. Give it a shot. Here we go. Try to keep the answer to yourself until I ask you, just so that everyone can check their work at the end. Sorry for what? It's okay. Don't worry about it. All right. Now, Fuad, what was the answer that you got for question D? Can you type it again in the chat, please? Perfect. So he got x equals 2 over 3. If you got that as well, type a G in the chat if you got that as well for question D. Okay. Hopefully you got that answer. And if you did not, let's talk about it. Okay. So first thing we're going to do is convert this into our exponential form. We get 5 to the power of x is equal to the cube root of 25. If you have the cube root of 25, any cube root or any root can be converted into an exponent that's a fraction. So our first step is to understand that a cube root is technically just 1 over 3. Once we have that, we're looking for a common base. We can write 25 in terms of a base of 5. So for us, that would give me 5 to the power of 2 to the power of 1 over 3. Then, using our exponential rules, we can multiply the two together, and that would give me my final answer of x equals 2 over 3, as Fuad stated. Very good. Perfect. Now for the last question here, there wasn't anything difficult about this. The only thing you had to be careful of was the negative in front. You can't convert it to your exponential form until you move the negative to the other side. So essentially we're just going log base 5 of 5 is equal to negative x. And that's what we're going to start with first. If you convert it beforehand, it's going to become a little weird because you have your negative in front of your exponential, which is not what you want. So we put the negative on the other side where the x is, then we can convert it to this, right? And this is just an exponent of 1, which means we get to a situation where we say negative x is equal to 1, which means x is equal to negative 1. And there's the answer there. Okay? So if you didn't move this over, you may have gotten confused. You're like, wait, I'm not getting the right answer. I don't understand what's going on. You just have to move the negative to the x first before you solve anything. And there's your answer. Okay? So I think so far so good. Most people are getting comfortable with solving logarithms. It looks like there's no questions in the chat right now. So that's pretty good. Now, this one's probably going to be the one that probably pisses off most people, only because you hate estimating and you're like, oh, this just guess and check. Yes, it is just guess and check. I'm going to be straight up honest with you. It is guess and check. Okay? So it sucks, and I'm not going to sugarcoat that in any way. But we still have to go through it because you still have to understand how can you approximate the value of logarithm to solve our answer, right? So when we take log 5 is log 5 of 47, right? And let's say we write that the same way as we did before, and that make that equal to x. The issue arises that we understand that it is impossible to write 47 in terms of base 5. That is impossible, right? It is just not possible. However, what we do understand is that 5 squared is in between or is before 47, and 5 to the power of 3 is after 47, which means we can approximate this number here to be in between a power of 2 and a power of 3. Okay? Because this is 25, right? And this is 125. So 47 must be closer to the end of 5 to the power of 2 than it is 5 to the power of 3. And what sucks is that you have to do the math now. Right? So essentially we literally just plug in, right? 5 to the power of x, where x is equal to a certain number. First we start off at 2, which we do 25. Then 2.1, 2.2, so on and so forth. And you can do this on a calculator, right? This is something you can easily do on a calculator and solve your equation. So if we do 5 to the power of 2.1, we get 29 point, rounded to the nearest decimal, I guess would be 29.4. Right, we'll round it as best as we can, and then doing it to the power of 2.2 would give me 34.5, and 2.3 would give us 30. What's it called? Let's see. 2.3 would give me 40.5, and 2.4 would give us 47.6, and I think we can stop there. We can go to 2.5 to see, and that would go straight to 55.9. And so the question was, what if we get the average between 3 and 2? Good question. So if you add 3 and 2 and divide it by 2, that gives you 2.5, right? Is 2.5 always going to be the answer? If you take a look here, I think this answers your own question, Matten. Is 2.5 the answer? It is not, right? And the reason for that is because this gap between 25 and 125 is a very, very big gap. And 47 is not closer to 125. It's rather closer to 25. And you need to find out exactly what 10th decimal gets you that closest answer. So if we had to go, it says round your answer to the nearest 10th. If we had to pick, it would probably be x is 2.4, right? X is approximately equal to 2.4. Okay. Probably like 2.37 or 2.38, but rounding it up is 2.4. So no, you cannot find the average all the time because you don't know where the number may lie. If I gave you something like 29, you know for sure that it's not going to be the average between 3 and 2, right? So it all depends on the number. All depends on the number. But it is a good question that you asked. Very good. So approximately 2.4, and that's essentially how you're going to be able to do something like this, right? You don't have a calculator. Your calculator is not going to help you with this. Right? You take out your calculator, you try to type in, you can't because it's base 5. So this is your only way of solving by guess and checking. Create a table, go through. Okay? So we'll do it one more time. This time we're doing log base 5 of 6, and it says round your answer to the nearest 10th. So if we do log base 5 of 6 is equal to x, then 5 to the power of x is equal to 6, and once again we have another base 5, so we know that 6 is in between 5 squared and 5 to the power of 1 and 5 squared, right? So it's somewhere in between there, and we know that 6 is definitely closer to 5 to the power 1, but we'll see exactly what the decimal is. So we create our table, same idea. We say this is x and 5 to the power of x. And so x, we're going to start off with 1, and then 1.1, 1.2, 1.3, and you essentially go through the list. So going through the list, 5 to the power of 1, we know is 5. 5 to the power of 1.1 gives me 5.87. I'm going to write 2 decimal places to see if anything changes. 5 to the power of 1.2 gives me 6.8. 6.90 rounded up. Sorry. And I think we can already stop there. I think we already passed our answer, right? I don't think we need to do 1.3 because that's way far off. That would be 8.1. So from here, we can see the nearest 10th answer would probably be 1.1. So x is approximately, or sorry, it should be squiggly lines. It's probably equal to 1.1. Okay. Will I give you a lot of these questions? No. This really is not a good display or accurate representation of your understanding of logarithms. I think it's more so the understanding of exponentials, right? As long as you know your basic exponentials and you have a calculator, anyone can do this, right? You set up a table, you go from lowest to biggest exponent, and that's pretty much it. So I don't really want to give too many of these questions. Now, before we do these next 4, we need to go through some special properties of logarithms that you need to know. I will go into detail with this next class with the laws of logarithm, but let's first go over the properties. So let's go over these 3 properties here. Okay, the first one, log a of 1. Okay, so I'm gonna write it out over here because I want space. So log a of 1 is always equal to 0, no matter what. Anything, any base is of logarithm and the answer is 1 is 0, right? Because we know that any base to the power of 0 is 1. So that's a basic property. That's something you already know, you've learned before in previous years, right? So the answer should immediately come true. Doesn't matter what the base is, as if the answer is 1 for the logarithm, or what's inside the function is 1, then the exponent must be 0. Very simple. This next one here, log a to the power of x is equal to x. And I think that makes sense. Inside is the base to the power of x, which means a base of a base in logarithm will just give you the exponent. And we're going to talk about that in detail soon. So this answer is literally just the exponent that's inside the logarithm. If the bases match, the answer is the exponent. And the last one here, a to the power of log a of x is also equal to x. And this is an inverse property, and I'll kind of explain that in a bit. Or I'll explain this tomorrow. This might be like, hey, how does that work? I'll be going over a logarithm tomorrow, and I will explain how this works in detail tomorrow. I promise you. Okay? So these are some basic properties you need to know, right, before you do anything else. Okay? So, now that we have that, okay, evaluate each of the following logarithms. So here, negative log of 100, base 10. You know that this is 100, so what's the exponent required to get 100 in base 10 is 2. So if we write it out, it would just be 2, which is negative 2. And that's it. Can you give you an example for the second one? Absolutely. So an example would be, let me try to get some space. I should have made a little more space here. So if you have log base 2 and 2 to the power of 5, this is equal to 5. And you can do that using the common base method that we did earlier. Right? If you put x here and you didn't know what it was, you can say 2 to the power of x is equal to 2 to the power of 5, and x equals 5. Right? So I can do that in a different way, just kind of showing you. If we do this, then we can convert that to this, which means this is true. Right? So that's where that rule comes in, that property. No problem. Very good question. Okay. So I'm going to give a couple seconds for people to copy this in case they enjoy or find this example helpful. But let's go back, right? So here, log base 10 of 100 is 2. Negative 2 is negative 1 times 2 is negative 2. And there's your answer. This next one here, very simple. Anything to the power of any base log. No, sorry, I keep on saying power. Any base of log that has 1 is 0. You're done. There's no other solving that you need to do. That's simple. It equals 0. This one here, log base 5 of 5 to the power of x is just equal to x. No other work there. That's your basic property as well. That second one we were talking about. And this one here, 6 to the log 6 of x, and then that should also equal x. So there's not really much solving for these four, right? As long as you know the properties and you know your basic exponentials, you should be fine with solving these problems. And that only means that you should understand what the basic properties are, and you should try to memorize them. Why is base 10 not written? So, good question. Base 10 is not written because our general number system that we use is base 10. So all logarithms without a base 10 written is, without 10 or is in base 10 is always not written. It's assumed to be base 10 because that is our number system. We have 0 to 10. 0 to 9 is our numbers, and that's 10 numbers. So the natural logarithm is base 10, so we don't write anything. Anything else that's not natural, so any other base, is written down. I shouldn't use the word natural logarithm, just base 10 logarithm. There's a different thing for natural logarithm. But yes, hopefully that answers your question. Any other questions before we go on to our last three questions at the bottom? Going once, going twice. Cool. Cool. Let's go down. So, solve for x and round your answer to the nearest tenth if necessary. So, looking at this first question here, you have 2 log 10, 0.1 equals x. We can solve this first, right? We can solve that first. So, converting that, what's the exponent for base 10? That gives me 0.1. That's -1. So on the left side, we know that logarithm is equal to -1, and so my final answer would be 2. And there we have it. So if you can solve that logarithm, you should solve that logarithm. Okay. For part B here, you have log base 2 of x is equal to 5. You can convert this into exponential form. 2 to the power of 5 is equal to x. And hopefully you know what 2 to the power of 5 is, right? So that equals 32. Very simple. So converting your logarithm into your exponential form, and you get your answer. And the last one here, our little tricky one here, log base 4 to the power of 9. Okay. This one is tricky. Remember, be careful with this one. So first step is moving the negative over. Then we understand that 4 to the negative x is equal to 9, right? And you have to understand that 4 to the power of 1 is in between 4 to the power of 2 for 9, right? So it's in between these two, and now you have to approximate it because you have no way of calculating 9, right? The tricky part here is that you can see that the power is to the negative x. So if your power is to negative x and your values have to be positive exponents, And that means your x that you're plugging in is -1, -2, -3, so on and so forth, right? So you can try to figure out what that is and just stick on a negative at the end of it. The final answer you should get for this should be, give me 1 second, I believe is -1.6. Okay, so you can try this table thing on your own. It's going to take a lot of time to copy down, but this would be your final answer for that. Okay, approximately -1.6. And with that being said, that's it. That's our lesson for today. We'll continue on with things tomorrow. Okay. So please keep your eye out later tonight for the worksheets for tomorrow as we talk about laws of logarithms. Okay. So hopefully that has been helpful for you and you enjoyed my lesson. Please let me know if I'm going too fast. Please let me know if I'm going too slow. Like, I would like to hear your suggestions and fix and kind of adjust my lessons so that it's something that's easy to learn for you guys and easily digestible. So if you have any suggestions, feel free to either comment or email me and I'll take them into account for future lessons as well. So just some quick announcements before we end the class. Number one, I have extended all your math space deadlines to this Saturday. So even the ones that were already due and you couldn't do it, you should be able to go back and do it if you haven't done it already. So please go back and do your math space. I have set the deadline to this Saturday, and then once that deadline is over, I'll be taking the marks and inputting it into Google Classroom. Okay? Only the ones, of course, that increase your mark. Number two, you'll be getting your culminating assignment on Wednesday. So Wednesday, I'll explain what your culminating assignment is, and I will also be doing a tutorial lesson. So if you have any questions on today or tomorrow's lesson, you can ask me on the live stream on Wednesday. And if you have any questions on the culminating as I hand it out, you can ask that question as well. Other than that, that is it for today. Thank you so much for tuning in. Some of you had very good questions, and thank you for responding in chat and interacting with me. Yeah, that's it. So everyone, have a good rest of the day, and I'll see you tomorrow, 2 p.m. Peace out.